So my name is Kevin Lawson. I'm a professional engineer. I have about 12 years of experience in consulting engineering. And then about 2 years ago, I founded Ripple, and we've been making the software that I'm going to show you today. We're going to start with the easy button. So the easy button has really changed the way I work, and downloads have really skyrocketed since we released the easy button. And it's been much better received than I had anticipated. And for me, there's a bunch of different reasons why. First of all, it handles a lot of the grunt work of setting up a project. It copies over levels and creates views. I don't like spending a lot of time on the project before I can even look at the base sheet, and the easy button just does that automatically. There's also a lot of projects that you don't want to spend a lot of time on, but you need to get the architect feedback. Like, if you know a project is going to change, you don't want to spend a lot of time running loads and doing all these things, but they still need the shaft sizes and the air handling unit sizes. So for projects like that, you can just hit the easy button, not spend any time on it, tell the architect what you need, and wait for the project to settle down before you really start digging in and making a lot of corrections. So it's really helpful to kind of push off the heavy lifting until you have a more realistic building. And the biggest one that I found is that I just find it so much easier to start with a design than start from scratch. It's so much easier to mark something up than start with a blank sheet of paper. And I don't really know why that is, but I just find myself on every project, I just hit the easy button, and then I know it's going to make bad assumptions, and I have the full expectation of just going back and deleting it. But it's just easier to start with something than it is for a blank sheet of paper. So let's go over an example of how the easy button works now. So we're just going to start from blank Revit. We're going to create a new project. We're not going to use any template, so we're starting from like bare bones scratch. First thing we're going to do is we're going to link in an architectural model. So here's a small school. The easy button does a lot of calculations, so it takes a long time to run. So we're going to do a much smaller school than standard, so it can go a little bit quicker for our webinar. But here it is. It's a very simple building, 2 stories, no windows on the top floor, very few windows. Very simple layout. And we're just going to go ahead and we're going to hit the easy button. And so what the easy button is going to do is it's going to acquire coordinates from this model, so you get your location and your building orientation for your loads. It's going to set this model to room bounding, so it'll take your space, so it'll take, so your spaces will be contained. And then it's going to copy over all the levels that you have rooms on. If there's a room on the level, you're going to need it in your project. So it just copies that over and creates a ceiling view and a floor view so that you can look at it. Now, sometimes architects go a little level crazy. So it doesn't copy over every level, just the level with rooms on them. And then basically it's just going to run the Ripple HVAC toolkit in order. It's going to set default settings. It's going to place spaces. It's going to assign occupancy categories based on the room name. It's going to look for internal loads. It's going to run loads. It's going to set default construction types, U values and R values based on the project location on the climate zone. Then it's going to zone the project. It's going to lay out diffusers and then select VAVs and place VAVs. It's also going to do 2 things that you haven't seen yet. It's going to place air handling units and shafts. So we'll just go through the pop-ups here. It's set default settings, new spaces. It's about a 10,000 square foot school. It assigned space types. So we've got some open offices. We have a gym. We have some classrooms. Pretty standard school. It didn't find any internal loads because I don't have an electrical model linked in. So it's just going to use the default space type internal loads. It's going to set climate zone 5 and marine 4 code minimum overrides. So this is in climate zone 5. It's going to round the CFM, it ran loads, and now it's going to drop an air handling unit on the roof. And that is something that we'll talk about. But you get a nice loads report here that you could look through, but I just find it easier to look at the schedules than look at this. So let's look at some outputs. So ceiling plans. So I copied over the first and second floor ceiling plans and made these for us. So we've got diffusers laid out in all the spaces. We've got VAVs selected. Note that it picked electric VAVs for this. We've got diffusers laid out, CFMs assigned. And how it does all this, the zoning, the VAV selection, the diffuser layouts, those are gone over in the webinar, and there's a link in the comments to all these. It's like an hour-long webinar for each of these components. So if you want to look and see all the assumptions made when doing that, you can go and watch those webinars. But we're going to focus on the new features. So the new features are going to be the air handling unit and then the ducts that are placed in the model. So let's look at all our schedules. We've got all of our schedules in here. Let's look at the air handling unit schedule. So this is just a generic air handling unit schedule. Nothing's actually selected. Just all of the inputs have been figured out from the project and just dumped into here. So notice, like, we know the total airflow, we know the outdoor airflow, but we don't know what the motor horsepower is. And the manufacturer just says generic here. Eventually this will say Carrier or Train or Daikin or Aeon, and it will have a real fan selection in here with a real motor horsepowers and real coil selections, real pressure drops, all that. But for right now, I just wanted to get something in there because it's helpful to get those generic sizes out to the architect quickly. So it drops, it doesn't make any like sense where it drops the unit. It just kind of drops it on a space in the zone. So that's always going to be wrong. So you're going to have to move that to where you want it. So let's just say here, we're going to move that to the middle of the building about. And then we can, you know, move the shaft ductwork over, and then let's see what that looks like. Okay, so here's the shaft size from the roof to the second floor, and then here's from the second floor to the first floor. So we can move that over too. Okay, so we can select this, rotate it. Let's see, and we'll put it right there. So really quickly, a couple minutes into getting the model, we can go back to the architect and say, look, here's what the rooftop unit, here's about how big it is. You can decide if you want to do screening or whatever. And we need a shaft about this size, you know, and so it gets really good information in there quickly. So yeah, let's dig in more to how we get these, how we get all this input information in. Now, this isn't a very exciting project to do air handling unit selections. It's just one, it's a small school, it's just one air handling unit. So let's switch over to the bigger school, the Revit, our Autodesk example project. So the way that this is going to feed data up into the air handling unit selection is based on the spaces in the zone. So that is what the auto zoning tool, this will assign zones. And the way it assigns zones is it uses the Ripple HU zone text parameter and the Ripple VAV zone text parameter. So the HU zone you could change just by changing this plan. So this will do it automatically. If it does something that you don't like, you can always change it by changing the text. Like if we want to change these two spaces from, you know, zone 3 to zone 2, all we do is select them, change them, And now that data will get fed up into the configurator. Let's keep this like this for now. So that's when you open up the configurator, it's going to pull all this data and combine it with a bunch of other data, and it's going to give you a pop-up here. Now, there is a lot of information that goes into here. So everything is collapsed. So it doesn't overwhelm you with information. A good thing to note here, well, first of all, let's go and let's talk about what I'm talking about when I'm talking about air handling units. So this is the default air handling unit that I'm selecting for. So this comes from ASHRAE 36. This has a sequence of operation associated with it. It's this flow diagram. The sequences have all been vetted by hundreds of engineers, implemented on a lot of projects. So it's really good to start with a base like this. Now, this can come in thousands of different flavors. Like, it might be a rooftop unit. You might have a rooftop unit. It might be indoor and you call it an air handling unit. It might have a gas burner as a heating coil, or it might have a hot water coil. It might have a DX coil. It might have a chilled water coil. You've got a million different filter options, but in general, this arrangement is what we're selecting for. Now, this comes out of ASHRAE 36, and in my opinion, it's missing a couple things that we're working on getting added. One being an ERU. So an ERU is required for the energy code in a lot of places and a lot of configurations. So we're working on getting this into ASHRAE 36, a pumped preheat coil for freeze protection, and a humidifier. If an ERU isn't required for the zone, the assumption is that there's just a separate exhaust fan. So not very complicated. But this is what we're talking about when we're talking about an air handling unit. So some people say rooftop unit. I just call everything, if it moves the air in a central VAV system, I just call it an air handling unit. So why are we starting with this as a system type and then at this configuration? So the first reason is that VAV with reheat systems are the most economical and efficient systems for most buildings. I mean, they really can be applied to a lot of different size buildings very economically and very efficiently. The International Energy Code requires economizers in most situations. So anything above 4.5 tons, you need an economizer. If you need an economizer, you need a way to relief. So you need a return fan, and you need to be able to bring in full outside air, full ductwork to each space. It also moves all the fans, filters, and motors out from above occupied zones. So it's easier maintenance. If you have fan coil units in a space, you got to kick the person out of their office. You got to climb up above the ceiling, get dust everywhere, to change filters 4 times a year, or to grease fans, or to change belts. And it makes maintenance kind of a pain. And those fans are noisy. So it gets all of that stuff up into a mechanical room or onto a roof or into a penthouse or something like that. It's got no refrigerant piping routed through occupied spaces. So if something happens and they put a closet in that you weren't expecting, you don't have to rework all of your piping to meet ASHRAE 15. And then the last reason is kind of independent of the HVAC engineering. It's just that Revit projects tend to skew a little bit larger. So a lot of the smaller projects where a different system would be better suited to, like unitary or VRF. A lot of those jobs are still done in CAD, and since this is a Revit tool, we want it to be be most applicable to Revit projects. Okay, so let's open up, go back to the AHU configurator. Let's pop down the project information. The first thing to note is that everything here is already set with defaults. So as you open all this stuff up, you already have temperatures and everything ready to go. Those defaults are what the easy button is going to assume. So when you open this up, just know that this is what the easy button assumed. So, actually, let me close this and reopen this so it goes back to default. So it's going to know, and so here's how it's going to make its assumptions. It's going to say if your total project load, if it's 0 to 100 tons, it's going to assume a DX coil, chilled water coil. If it's 100 to 300 tons, it's going to assume a chilled water coil, but an air-cooled chiller. Greater than 300 tons, chilled water. Heating source selection. If natural gas is available, so it's got a utility database in it. It says, hey, if natural gas is available from 0 to 1500 MBH, put a gas burner in. If not, put electric. And if it's greater than 1500 MBH and gas is available, it's going to pick hot water, and it's going to pick a humidifier, anything above zone 3A. So that's how it's going to make its assumptions for the easy button. So when you hit the easy button, you can kind of know what it's going to be assuming. And you'll see here, this project dropped in hot water VAVs because the load is bigger than 1500 MBH. Whereas this project dropped in electric VAVs because the load is under 1500 MBH. Now, if that's not the right assumption, you can just delete these and reselect them with the VAV tool for hot water. But again, for me, it's easier just to it's easier to decide to switch than it is to decide to make the decision from scratch. So at least I've got, I'm in the ballpark of what the right equipment selection is. And as you open this, all of those assumptions are going to feed through. So it's going to pull the project latitude and longitude from the project. Now, this was brought in from the architectural model when you acquired coordinates, or when the easy button acquired coordinates. Then it's going to find the 10 closest ASHRAE weather stations and give you the option of those. The easiest way to do this is just to set this right in the project. But if for some reason the architect doesn't, they normally do. But if they don't, you could just change these lats and lawns manually, or you can just pick a different state and county, and these will update and give you new options on your weather stations. It also gives you some information about the weather station to help you make decisions on which one to choose. I mean, typically the projects where you're working, you kind of know what weather station you choose. So as long as you're in the ballpark, you can pick from the drop down here. But let's say the Manchester-Boston is 4.4 miles away. The station's at 220 feet, which is about the same as this. So as I change, I could see that starts to get farther away. So now it's 15 miles away. But this has a lower dry bulb, design dry bulb temperature. But let's just go with the closest one. So Manchester-Boston design dry bulb temperature is 1.8, humidity ratio is 2.7. I could change the frequency of occurrence and watch this change, 1.8 to 7, or I could just enter my own values, whatever I want as custom. Same goes for cooling, 91, 71.6, 88, 85, or enter customs. So that's your outdoor air conditions. The indoor conditions, we put this here so we can figure out what the return air temperature is. So we could do the mixed air calculations and select our coils. So this is just generic. What zone is the temperature? So 70, 74 is pretty good. Most importantly is setting if you're going to humidify the building or not, and what humidity you want it at. Again, anything above 3A, I'm going to humidify. So by default, that's going to be set to humidify for everything north of climate zone 3. Okay. Now let's get into the air handling unit components. So filtration. So filtration, we're going to have filters here, here, and here. And so for the AHU, you might have pre-filters and final filters. For the ERU, you probably are just going to have one set of filters. So by default, the ERU outdoor air is just going to have a metal bird screen side load, and it's going to have no filter on the exhaust stream. You might want to change that. It's really up to you. By default, the pre-filter is just going to have a combination pre-filter, bag filter, just in one section, and it's going to be MERV 8, MERV 13. If you want to change that, let's say we want a real pre-filter, we'll do a side load, flat 2-inch MERV 8. And then for our final filter, we'll do a front load HEPA. And we'll put an access panel in there so we can get in and change these things from the front. So these are just common filter configurations. You can pick them. Once these are in the schedules, they're just text parameters. You can override them to say whatever you want. But this just kind of gets you thinking, because these selections affect the pressure drop of the fan. So you need to get these in here before we get fans selected. Okay. And so on to fans. So we've got fans here, and this is where we start to pull in data from the Revit project. So here's the sum of the total area served of the air handling unit. And here's the sum of the specified supply airflow on all of the spaces. Now this is going to be the sum of the peaks. So this is what it's going to assume by default. It's not going to assume any diversity. And I'm probably going to talk about diversity and safety factor here in a second, because it's a pretty important assumption that I'm making, especially on the easy button. But if you ever forget what any of these things are, you could just hover over the top and it'll give you a pop-up reminder of what all this stuff is. So let's talk about diversity versus safety factor. So safety factor in HVAC design can be problematic for two big reasons. So a lot of times safety factors can kind of cascade and cause issues. You know, each engineer adds a safety factor and the equipment just gets bigger and bigger and bigger and bigger. So for example, the intern might, when he's running loads, they might take a safety factor on the U value of the glass. And then he hands those loads off. The engineer that's reviewing those loads doesn't know that they took that safety factor, and they might add another safety factor to the loads. Then they figure out the airflows and they hand that off to the principal, who talks to the rep, and he might want a little bit bigger than normal equipment, so he adds a safety factor on the airflow. Then whoever's doing the chillers looks at the air handling unit schedule and takes a safety factor on that, and now all of a sudden you've got chillers that are 3 times the size they need to be. So I don't have a problem with taking a safety factor, but just know where you take it and take it in one place. And in most engineering disciplines, that's not a problem. In structural engineering, if you take a big safety factor, your building just gets stouter. It doesn't hurt anything. But that's not true in HVAC. Oversized equipment really can hurt a project. It uses too much energy and it has poor performance. Best example is a DX unit that's oversized. If it's cycling on and off, if it only is on for a few minutes every hour, the rest of that hour it's just dumping unconditioned humid outdoor air into the space, and it could cause a big problem. And typically these diversity and safety factor just cancel each other out, really. So let's say you have 10 rooms, the real load with no safety factor comes out to 800 CFM per room. If you don't take diversity, you size the air handling unit at 8,000 CFM. Now let's say you take those same 8 rooms, but you take a safety factor and you get 1,000 CFM a room. Well, now you take some diversity and you end up with the same size air handling unit, but now you don't know how to balance this. How do I balance 10 rooms at 1,000 CFM a room with an 800 or 8,000 CFM fan? it's just, it makes it a little bit more confusing, and it really isn't saving anything. So the key takeaway here is the easy button assumes no safety factor and no diversity. So if you know that going in, when you see the easy button, you know, hey, my air handler is going to get a little bit bigger or a little bit smaller, or it's going to stay the same size. You could always go back and you could add these things in manually. And here is a, just kind of a way to add that stuff in manually. If you want to take diversity, maybe you calculate this separately, or you just know what diversity you want to take. You can do that, and it's going to recalc these supply airflow values based on that. And it's also, just for sanity, it's going to give you a CFM per square foot for each zone. Now this looks like 1.75 CFM per square foot, 1.8, 1.5, 2. That looks a little high to me, but if you look at this building, it's a giant glass rectangle, which is pretty in vogue. So it's probably more in the ballpark than if it came out at 1 or 1.2 or something like that. So that looks reasonable. Exhaust fan, again, it's just the sum of the specified exhaust airflow on the spaces in that zone. Then the return fan is the specified return airflow. And then the relief airflow is the supply air minus the exhaust. You pick the bigger of those, and you get your return fan size. Now that feeds forward into the ventilation calculations. Now, just like the supply fans, the ventilation calculations query all of the spaces and pulls all of these numbers up into this project. So the number of people, the area times the ventilation CFM per square foot, the number of people, and the people per square foot. For ASHRAE 62.1, though, they want you to take what is the total system population? So you have people moving all over the building. They're either in their office or they're in a conference room, but they're not in both. So they want you to take an occupancy diversity factor to calculate the outdoor air intake of the unit. So that's what these numbers do. Again, you can look these up in ASHRAE 62.1, but that's all how this is all calculated. Your system ventilation efficiency is calculated here based on the diversity. And then you finally get your outdoor air intake here. We also pull down the supply airflow here so we can get a percent outdoor air to make sure that looks reasonable. Just another sanity check. And now this all passes down into the ERU information. So the ERU, now we take that ventilation information and we pass it down into what our outdoor air is for the ERU. And we'll just go back and look at this. Your outdoor air is coming through the wheel. You've got your exhaust air going out the other side. And that's what this is set up for. So pulls ventilation data from the ventilation tab. And then it pulls your outdoor air conditions from here. So if this changes, let's say we want 99 and 2%. Now it changes here so we could figure out what our ERU discharge temperature is. You'll notice that only one of these zones gets an ERU, that by default. So that is because, go down to the ERU. Here is the International Energy Code requirement for ERUs. So if you have exhaust air that is at least 75% of the outdoor airflow rate, then you look at this table to see, do I need an ERU? So we are in climate zone 5A. We are a 43,000 CFM air handling unit, and we have 11% outdoor air. So climate zone 5A, we're between 10 and 20, and so we need an ERU because we're above this 26,000 CFM. So by default, it's going to say, hey, you need an ERU for this unit. Now, if you don't want an ERU, you could just uncheck the box and it won't drop one in. But that's assume we want an ERU. So it's good to know the discharge conditions of that ERU. And for that, you need what the exhaust air conditions are. That all gets fed down from these set points. So how this exhaust air conditions get calculated is it takes these values, and then it adds the unmet load. So things like plenums, things that have loads but don't have airflows assigned, it adds that airflow to the total return and exhaust airflow to try to figure out about what the exhaust conditions and return conditions are going to be. So the exhaust air is always going to be a little bit above or a little bit below, depending on what the unmet load is. If you don't have any plenums, they might be the exact same. But it allows you to account for that heat loss somewhere. The other thing you'll notice for ERUs is that you have a wheel, in the winter, we have a wheel frost threshold. So as your heating conditions get more and more humid, that wheel's going to pick up moisture and it might freeze when it hits this cold outdoor air temperature. So at these conditions, the wheel frost threshold is negative 4.3 degrees, but that's above our design temperature of 1.8 degrees. So it's still gray, so it doesn't have a problem. Now, if I say at the beginning, when I'm setting my conditions, if I say, I really want to jack the humidity up on this building, up to 50%, now it's going to say, hey, your wheel frost threshold is 10 degrees now. That is above your 1.8 degrees. You need to do something about freeze protection. You could shut the wheel off, you could do bypass dampers, you could do all kinds of stuff, but it's just a good check to make sure that you don't account for this load when you're sizing coils. Let's take that back down to 30. This gives you just some generic efficiencies for generic equipment to be able to calculate approximately what this after ERU outdoor air conditions are. So it's bringing this outdoor air in the summer from 90 to 80, and it's bringing it up in the winter from 1.8 all the way up to 50. So because we've got a lot of exhaust air, we actually have more exhaust air than supply air. It does a really good job. So then this information gets fed down into our heating information. So we've got three options: electric, gas, and hot water. So we already talked about why this chose hot water, and this is the default selection, is because it's bigger than 1500 MBH and natural gas is available. You might need to check those assumptions. It's also going to say, hey, I'm going to use my ERU discharge conditions for this because my wheel frost threshold is low enough. Now, if I go back here and I say, hey, let's really humidify this building tough, then it's going to say, oh, I can't use this anymore. That's use just the outdoor air. We're going to assume the wheel shuts off. So that also helps, as you're setting this stuff, it helps give you a good selection without thinking about it much. But assuming we want to use the discharge conditions, the ERU discharge conditions, it's going to take that outdoor air from the ventilation calculations, mix it with the return air, and get a mixed air conditions. Now in heating mode, since this is a VAV air handling unit, the airflow at heating is going to be lower than what the total supply is. So the way it's going to try to figure that out is it's going to go to all your price VAVs that you have in the model, and it's going to pull the heating maximum airflow and sum them up in that zone and set that as your mixed airflow. If you don't have VAVs in the model, it's going to just take the space ventilation and times it by 1.5. So it's going to try to get you in the ballpark here, so you can calculate realistically, what temperature do I have hitting my coil in heating mode, because that drives your decision on how you want to handle freeze protection. And there's a bunch of different ways to do that. So here I've got some some VAV or some air handling units entering air is 36, 41. Let's say that the ERU breaks. So I'm down to 47 here. But these are getting pretty close to freezing, and I do not want to freeze my coil. So I've got a couple options. I could add glycol. And enter glycol percentage there, or I could pump my preheat coil. Now, if you add glycol, it's hard on your pump efficiencies and boiler efficiencies. So I like to just pump the preheat coils with plain water. And so here's kind of a detail of what that looks like. It allows you to set your velocity so you really push some water through these coils and you don't get any cold spots in the coils and you don't freeze the coils. The best, what that velocity should be, the tube velocity, the best I've seen is, this is from the VA Veterans Affairs Hospital Design Guideline, and they say 3 feet per second, which I think is pretty reasonable. And so that's what I go with by default, is 3 feet per second on preheat coils. Then you can enter your water conditions, max air pressure drop, max water pressure drop. Same thing for gas. You know, you calculate your mixed air. All of this is all the same, except for you've got a little bit different information to enter in, what modulation you want, what efficiency you want, what gas pressure you have available. And then electric is, how do you want to modulate it? What's your voltage? What's your phase? So now you got all the inputs that you need for your heating. Humidifier takes that heating discharge information. And the mixed air humidity ratio, and allows you to set what you want your zone condition for humidity to be. So if you have one zone that you want a higher humidity than another, you could change it here, and it'll figure out, hey, what do you want? What does your discharge conditions need to be to get there? And then again, it'll try to warn you if you're doing something crazy, like if you want to go 74 degrees, 50% relative humidity, it's going to say, hey, I need a lot of humidity and I'm going to exceed 90% at the discharge. So it's going to warn you there that, hey, maybe you need to bump this discharge air temperature or lower this back to a reasonable, more reasonable number for a humidifier. Again, if you don't want to provide a humidifier, you can just uncheck these. No problem. Cooling, much the same as heating. You figure out your mixed air, except for now you're at full flow. So now you've got a lot more return air. Your outdoor air gets pulled down. You do the mixed air calculation, and you figure out what your mixed air conditions are. And your mixed air calculator is a mixed air psychometric calculator. I don't know if I already went over this, but air doesn't mix proportionally to temperature like water does, so you have to do some more calculations. Really only enthalpy and humidity ratio mix in proportion to the mass flow rate. So these numbers might not look exactly proportional to the dry bulb temperature, and that's just because air doesn't mix that way. But this figures it all out for you, so you get a real coil inlet temperature. And these actually look like pretty standard inlet conditions for a coil, about 78, 63. Then you tell it what your leaving conditions want to be, and you've got all of the inputs you need. So, like I said, this is just, I'm not tied in with a specific manufacturer selection software yet. So this is just picking generic air handling units that are just based straight up by the CFM. So I think it just does like 500 feet per minute, and it picks a box size from that airflow. So I'm going to hit select AHUs. It's going to tell me, hey, I put 1 on the 3rd floor and then 3 on the roof. And you see they're just dropped in, not in a great spot, but just in like the general locations for those zones. So if we look at the third floor zone, here they are. And then we look at the roof, they're kind of all over the place. They're hanging off the building. Doesn't make a lot of sense, but I could put them now where I want them. So this is the air handling unit that came with the ERU. The ERU is a separate entity behind it. So we'll move that. See, it placed these right on top of the skylights, which obviously doesn't make any sense. So we're going to move it. This one didn't get the rotation really right. So we can move that. And so you see really quickly, we can be showing the architect about generally this is what you're going to have on your roof. Or if they want it in their basement, you can move these to their basement. Or if you want them side, you can move these around however you see fit. But at least you've got a good size. Now, once you get them on the level that they should be going on, now I know where the air handling unit is, and I know what all the level airflows are, so I can start dropping in the shafts. And this is what, again, this is what the easy button does just at the end. It just places shafts. So we're going to hit place shafts, and it's going to drop some ductwork sized for the load just right underneath the air handling units, and then allow you to mix, to move these to where they go. With this stuff, with air handling units, with shafts, it requires architectural coordination. So I'm never going to know without architectural coordination where these go. So it's going to be up to you to put these into a reasonable spot. So it looks like the architect wanted that to be a shaft. So we can take these ducts, we can move them over here. So it's going to assume you're ducting the return, even if you're just going to use the shaft as a plenum. But right now we could say, hey, we're a little short on the shaft here. So maybe we could delete the return ductwork and just use the shaft as an open return. We're still probably a little short. The bathrooms are right here, so I've got the exhaust duct right there. That's good. So now I've got these. This shaft that serves this big open. Big open spot right there. You know, at least we're talking about this very early in the project of where do you want these shafts to go? Do you want it to go behind this? Can we move this door? It's much easier to have this conversation on day one than one day before the job goes out. I've had both of those conversations, and I know which one goes a lot easier. These ducts are just sized at 0.1 inches per 100 for every floor. So again, if your assumptions are different, you could change the duct size. The shafts are pretty dumb right now. It just does 0.1 inches per 100 feet, and there's no fittings because I don't know what fittings are available. There's no smoke dampers, there's no fire dampers, there's nothing like that. But they do step down as CFM comes off the shaft, so we can look at that. So you see it gets, you know, after we come out, after we serve the third floor, we can go to a smaller duct. So we're going from a 70 by 36 to a 60 by 30 to finally the bottom floor only needs a 60 by 18. So it'll give you reasonable sizes, but it doesn't attach them with any fittings. Now, if you have fittings in your duct, you could just connect these and then your transition will automatically drop in there. But I don't have the fittings or fire smoke dampers or anything like that worked out yet. So right now it's just generic sizing information for that. Okay. Trying to think if I'm missing anything. So this is that small school. This is right after the easy button's been ran. You've got VAV schedules all ready to go. You've got air terminal schedules all ready to go. Everything's sized. You've got ventilation calculation schedules figured out. You've got load schedules. You just have a lot of good information with just very little work. You just have to go back and check the assumptions and fix them as they go.